Hi everyone, my name is Evangelos Daravigas and I'm a student of the Cybersecurity Master's Degree program. The topic that we are going to discuss today is a cyber defensive industrial system with redundancy and intrusion detection. During the past few years, the industrial control systems, also known as ICSs, and control systems automation has brought more and more control systems interconnected. The information enhancement has also inevitably created cybersecurity vulnerabilities. Modbus TCP is an example of such a system. Moreover, the security techniques and methods that are being utilized in traditional information and communications technology networks are rarely implemented in ICS networks. The goal of this paper is to present a new way of providing monitoring and intrusion detection for an ICS environment by leveraging the existing operation-based defensive architecture control system approach with the addition of a new mitigation technique which uses SNORT as an intrusion detection system, which is also known as IDS. Before jumping into the topic of the presentation, I would like to share with you my acknowledgements for the authors of the paper, Dane Robinson and Charles Keane of the Electrical Engineering and Computer Science Department of the Howard University. The paper presented here was published by IEEE in the North American Powered Symposium of 2017. I have also included a link to the paper here for quick access. The agenda we are going to follow is according to the chapter outline in the paper. First, we will have a short introduction to the topic with providing some background information in order for everyone to be on the same page for the discussed topic. Following that, we are going to discuss how monitoring and intrusion detection can be achieved. Next, the presentation includes an experimental setup on the defensive architecture that existed prior to the paper production. Two attack vector scenarios are presented. One, an internal attack to the primary controller via the compromised control engineering workstation, and the other one is a remote hacking to the control system. Following that, we are going to maintain the existing setup by adding the bus monitoring feature in order to tackle the weaknesses of the previous implementation. Finally, we are going to focus on the conclusions, what the paper is all about, and what we actually achieved with that. Introduction. Modbus is a communication protocol used in control networks. It was originally published in 1979 by Modicon, and at that time it was designed to work over serial links, such as the RS-232 and RS-485. Ever since, it has been the most commonly used protocol for PLCs due to its robustness and simplicity. Due to the current needs, the Modbus control network is now connected through the Internet to corporate networks in order to enable remote access to the control network and therefore to the control devices. This configuration of no air gap control network is vulnerable, bringing threats towards both the planned operation but most importantly towards public safety. An example is included later in the presentation to make this case quite clear. Moreover, currently, the Modbus protocol lies on layer 7 of the OSI model. This can also be observed here. A Modbus TCP packet would include information related to the Modbus protocol, for instance, which registers need to be involved as long as what kind of operation is being sent, and the information of a typical TCP packet, such as the IP address, the port, and the MAC address of the device to which a packet is being sent. Transmitting a Modbus TCP message introduces high levels of complexity when it comes to the reliability of message delivery. This is due to the fact that such an operation must be done in real time and of course properly. It is a fact that the most important security objective for industrial control systems is its availability. We also mentioned that the Modbus protocol was not designed to be connected to the Internet, and this has a result has as a result further limitations which can be potentially exploited by attackers. An attacker can perform, for instance, a man-in-the-middle attack, a denial of service attack, a replay attack, as well as unauthorized command execution attacks. Prior countermeasures involved the application of a diversified defensive control architecture and operation-based resiliency measures in order to secure failover and fail-safe modes of the control systems, even in the case of a compromised system. However, the weakness of such system is introduced when the attacker intentionally is not making any modifications and the hacked devices operate closely to the desired behavior. As already stated, the goal of this paper is to encounter this weakness and to provide both cyber infiltration as well as intrusion detection to the ICSs. The up to the paper conduction operation-based defensive architecture control system comprises of an isolated from the communication network duplicated controller in addition to the networked primary controller and the supervisor which monitors the signals from the functionally identical to controllers. Those are one primary network controller and the other isolated secondary controller with the same or safe mode functionality of the primary controller. The supervisor also controls their outputs. Each controller sends actuation commands to the isolated supervisor device. The supervisor examines both commands to determine if either is erroneous by comparing the commands to a database of known sensor values and corresponding actuation commands. If an abnormal output signal is provided by the network controller, the supervisor switches to the isolated secondary controller and sends a unidirectional alert message via the Internet through a specified open port to alert the remote management system that a potential cyber attack is present. Modbus monitoring and intrusion detection. By now, it should be quite clear that the operation-based defensive architecture control design, even if maintaining failover and resiliency, is still vulnerable to undetected intruders. The cyber attack on the SCADA system of the Ukrainian power grid in December 2005 is a recent example of an ICS attack. The investigation and forensic analysis of the firewall logs showed that the intruders had gained access to the network months in advance of the attack. Therefore, it was the attacker's intention to do reconnaissance in order to launch a coordinated and sophisticated attack. The addition of an intrusion detection system as another layer of defense could potentially prevent such an attack. An intrusion detection system, an IDS, is a system designed to detect attacks and malicious traffic on a single host or network. It can be placed on various positions within the network. It can be positioned directly on a network device, such as a switch, a router, a host device, or it can be placed on a dedicated device. An IDS can trigger an alert when an abnormal activity is observed in the network, or write this alert to a log file which is being monitored by a network system administrator, or automatically when it is being scanned by a script. Snort is an IDS. Snort is versatile, it's open source, and is supported by numerous operating systems, including Linux. Snort can operate in network intrusion detection mode to match the traffic against predefined rules and signatures. As mentioned already for any IDS system, when any suspicious traffic is being detected, an alert is being triggered, also for Snort. The detection of abnormal activity requires the definition of what is defined as normal for the network traffic. This can be achieved by two methods, the statistical anomaly or rule-based detection. The statistical anomaly detection is based on network traffic patterns and user behavior, which are used to form a baseline of the system. The statistical anomaly technique can be further split into two categories: profile-based and threshold-based. The profile-based detection forms a baseline for what is considered as normal traffic, meaning that the network traffic is being profiled based on its parameters. The threshold-based detection defines a threshold for the number of times a user may execute a particular action or the number of times that a certain type, say Modbus TCP traffic to port 502, of network traffic can traverse the network. In both cases, an alert is generated if a user exceeds with the traffic is generating a predefined threshold. The rule-based detection, on the other hand, is based on a set of predefined rules to identify whether an attack or intruder has made any traffic. The rule-based technique can also be split into two categories: anomaly detection and penetration identification. The anomaly detection is using rules which are produced by reviewing previous attack patterns or signatures of traffic that were malicious, and the penetration identification is using rules that have been conducted by security experts. Assessments of the control systems of defensive architecture without bus monitoring. This is the actual physical setup as it was done by the authors of the paper. With number 1, the network switch is used to connect the primary controller to the Internet. The primary controller and the supervisor are presented by Raspberry Pi main computers, as shown in number 3 and 4. The secondary controller is represented by an Arduino microcontroller, which is network isolated and performs the same functions as the primary controller. The network server is a laptop computer running Microsoft Windows operating system with the LAN interface connected to the Modbus control network, and the wireless LAN adapter interface connects to a Howard Wi-Fi network. The Remote Energy Management System, EMS, is represented by another Windows-based laptop which is connected to another Howard Wi-Fi network. Those components are not depicted in this figure. The hacker's computer can be either a computer that is connected to the internal network using its IP address space, such as the one of the engineer's computer, which is shown here as number 5, or an external to the network IP, such as the hacker's computer, which is depicted here with the number 6. It depends on the attack case scenario. The firewall rules of the supervisor are sending an alert message via the Simple Network Management Protocol, SNMP, to the management system in case an abnormal output from the primary controller or an intruder is detected. The sensor is represented by a dual inline package, a deep switch. When the toggle position is changed, it simulates a range of conditions from the field device. The sensor is physically connected to both the primary and secondary controllers and the supervisor. The LEDs give a visual indication when signals are being sent between the three. We will see an example of it in a while. The command for actuation is given only after comparing the controller signals against the operational database. The Raspberry Pis are connected in server-client architecture with Raspbian operating system installed on both. The Modbus simulation of client and server devices is implemented with Python scripts. Modbus TCP communication follows a master-slave architecture and includes 4 types of messages. These are the request. The request is a message sent on the network by the client to initiate a transaction. It could be similar to SYN packet for the TCP protocol. Indication is a request message received on the server side, similar to the SYN-ACK packet. A response is a response message sent by the server, similar to the ACK, the acknowledged TCP packet. And confirmation, which is a response message received on the client side. It cannot be explicitly similar to an existing TCP flag, maybe something like ACK to ACK. Two attack cases are being examined. The internal attack is simulated by creating excessive Modbus traffic using pings and function code read commands. And the external, in which the intruder gains access to the engineering workstation, the EWS, and via remote desktop is able to connect to the Modbus master and slave control devices. The detailed setup can be also reviewed in the paper. This is a screenshot of a session of Modbus TCP communication. Modbus request is initiated by the supervisor Raspberry Pi. A fun fact, it seems that the figures of the paper have been wrongly listed or listed in the last moment, and therefore all the figures are decreased by 1 when being referenced. In detail, the hacker acquires the credentials of the manager's computer and uses the built-in Windows RT remote desktop application to successfully connect remotely to the network server. The hacker then launches another remote desktop connection to connect to the primary controller, which is the intention of the hacker. After entering the credentials and gaining access to the application, he or she can modify the settings of the primary controller. So the hacker creates two scenarios: the modification of the primary controller settings and no modification. During the first case scenario, the operational-based defensive architecture control system detects with the supervisor the abnormal activity and quickly switches control to the secondary controller. However, when the intruder is making extremely small or no changes at all, the operation-based defensive architecture control system does not detect any suspicious activity. As we stated previously, the LEDs give a visual indication when signals are being sent between the three components of the setup, the supervisor and the two controllers. Here the indication represents that a large change has been detected. This in regards to the first case scenario, and therefore a hacker presence is assumed. Concerning the external attack, due to the fact that the activity of the attacker remains the same in both of the cases, the results remain the same as well. The operation-based defensive architecture control system is able to detect that the compromised system is being used. You may refer to the number 5 of the listed references for more information regarding that. However, the intrusion of the second case still remains undetected. The operation-based control system alerts are being appended to the auth.log file. However, as it can be observed here, no alert regarding the suspicious behavior has been logged when the operation-based control system is being used. Verification of the control systems of defensive architecture with pass monitoring feature. The same hardware setup is being maintained. The only addition is that of Snort. Snort is configured with rules for signature and anomaly-based intrusion detection. Snort rules are configured to send an alert if an external IP address tries to send an ICMP ping command or access the network. Modbus controlled data bus network traffic was also gathered in order to define the normal traffic behavior using Snort, once again, which logged over the time which maintained locked over time and used to set the threshold values for anomaly-based network traffic rules and alerts. Snort is being set to Network Intrusion Detection System mode, NDS mode. In such mode, the snort is remaining undetected by the attacker. Newer versions of Snort have been developed to include preprocessor modules for use with SCADA system to support the use of Snort with the Modbus protocol. Additionally, Snort can also trigger alerts based on errors of the devices, which can be used for troubleshooting purposes. The snort rule presented here will check the byte at the 8th position. This corresponds to offset 7, which contains the Modbus function code. The rule will therefore check the function code of Modbus TCP traffic going from the client network to server network for function code 2, which is read discrete input. If the function code of the traffic is examined and a non-bus discrete input command is detected, then an alert will be generated with the message Modbus not allowed funct attempt, indicating a suspicious access attempt. Since the Modbus is typically static, the alert all strategy can also be used, which allows easy monitoring. In this mode, a representative baseline is formed for comparison purposes, defining the normal traffic patterns. This is how a snort rule is configured. A text editor like Vim or Nano can be used to set up new rules to modify the existing ones. The rules are by default deployed in the custom.rules file in the /etc/nort/rules directory. As you can see here, further rules have been implemented for each case. The first rule indicates that an IP, whether internal or external, is attempting to read multiple registers of the PLC, and therefore an alert is being triggered, as this might be an attempt of an attack. The second rule is regarding a potential attack by an external IP address, which tries to send a ping command to the protected network. The last rule is the one that we have already discussed. This is an example of snort rule alerts being generated and logged when an unauthorized function code is attempted. The deployed snort rule detects traffic originating by an external IP address. Simultaneously, or even earlier, snort sends an alert to the management system based on an increased level of control data bus traffic, indicating the possibility of an intruder. Snort detects higher than normal levels of Modbus traffic, and therefore this finding makes the supervisor switch the control system from the primary controller to the secondary and send an alert to the management system. This is also an example of snort alerts being generated and logged. In this case, an external attack attempt is being detected, as it can also be observed by the logging of the ICMP protocol. In this case, the supervisor immediately switched to the secondary controller. One more suggestion by the authors concerning the logging of the alerts is to append the alerts to the auth.log file of the system with a timestamp and priority severity level in order to be further analyzed if needed. This can be also extremely helpful in cases of troubleshooting and forensic analysis. This file should be accessed only by the root user of the system in order to provide one additional line of defense to the monitoring and information integrity of the system. A standardized period of reviewing as long as a Python script to switch the control to the redundant control may also assist to that procedure. Since an external IP is detected by snort, an alert is being sent and the supervisor immediately switches to the redundant secondary controller for the external attack case scenario. We can see here that when a snort verifies the presence of a hacker, it automatically sends also an email notification. Conclusions. To sum up, securing an ICS is challenging due to the cyber vulnerabilities that exist and come within the Modbus protocol. The operation-based control system is not able to prevent the intrusions that remain unaware and undetected, even though we can still have resiliency and fail operate of the system. However, we can still tackle those weaknesses by implementing Snort as an additional line of defense. With Snort, as we saw already, we can detect intrusions that remain intentionally undetected, as well as possible equipment malfunctions and software glitches with handling the respective error codes. What we achieved is that we have, in the end, a truly resilient and secure control network. These are the references as listed in the paper. I have included them also here for your convenience and in case anyone would like to find out more about the topic. Feel free also to reach me out to Piazza to discuss anything related as well. Thank you everyone for attending my presentation. Please subscribe to my... No, I'm kidding. I would be more than happy to answer all of your questions on Piazza. Thank you everyone.